Okay, my name is Justin Moll, and I am the Director of Marketing at VadaTech. Today I'm going to talk about some of the advances in digitizers and how they're advancing some of the Moll Aero and physics applications. I'm going to try to use my pointer without falling off the stage here. We'll see how that works.
By the way, this is Justin's excited voice.
So actually the slides are a little cut off, but I'm sorry, what? Both screens at the same time? That's going to be a tough one. I'll do my best. So we've had some of the architecture wars over the years. We've had some of the architecture wars over the years, and VME and compact PCI, and then the fabrics came, and so on. We're talking about some of these very high-end digitizers, different converters. Here we're going to focus more on micro TCA and VPX. For VadaTech, actually, we use both VPX. We have some specialty products for VPX, but our architecture of choice is micro TCA, largely because of the size. I'm going to slightly get out of the frame here. Largely because of the, you can see the size difference from the front panel point of view and from the side point of view. Get a lot of performance density. So for some of the digitizers that are coming out, we'll look at putting them on FMC module versus an AMC module. And with the kind of performance that you get now, you could really pack a lot of punch in a very small space. So looking at the FMCs, you can see, for example, you have a DAC at 5.8 gigasamples per second and at 12 bits. And that's actually in a mixed mode, a dual mode there, so it's 2.8 ramped up at double speed. And also a A to D converter at 4 gigasamples per second. So on the FMC, you can see you basically have the converters, but you also have the clock and jitter cleaner and the main ports out the front. So, you have a certain amount, but you have that flexibility of the FMC, of using that FMC in different modules, different applications, even different architectures. You could use that FMC in AMC, VPX, whatever the architecture is. If you take this same part here, it's actually on AMC, you're taking the front end, but you're also adding the whole back end. There you're adding the FPGAs, could be Vertex 7, any of the different types of FPGAs available out there. You also have the clock and jitter cleaner. This is very nice as you could have the dirty clock across the back plane, have it run through the PLL on the jitter cleaner, ramps up the speed much higher so that difference, that jitter really just gets minimized. It just becomes a blip on the scope, and you run it back out so for a clean signal. You could also put different banks of memory and IPMI controller. One of the nice things about AMC micro TCAs, you have the inherent system management, so you have the IPMI controller on the system. And memory is often application specific, but you do need a certain amount of memory for the buffering and so on. So there's a lot of flexibility, a lot of different things you could do in a little bit larger form factor for AMC. So if we're combining the two between the first case and the second case, we had inherent FPGA in one. Here, we're actually combining the two pieces for an FPGA carrier where you put the FMC on top of the FPGA carrier itself. So in this case, I'm showing a dual FMC carrier, but in the photo, I'm showing a single. So the photos aren't exactly matching up. I'm trying to show some different scenarios here. But again, you have the FMC, you could have all different types, again, with the flexibility of FMCs. And on the back end is where you could put, different types of FPGAs, clock and jitter cleaners, and so on. So here I'm showing off my Visio skills. It only took me a couple hours to do that. That is supposed to be a 3U chassis, believe it or not. So basically trying to show with these very powerful digitizers now, you don't need the big racks, you don't need all the space. You could pack a tremendous amount of punch in a very small space. So let's say it's a radar signal processing application. You have a chassis that is a MOSA, modular open standard architecture chassis, backplane based, with 6 AMCs inside there in just a 1U profile. You could have that ruggedized to MIL-810 and 901D for shock and vibration, 461 for EMI, all in a 1U chassis. Now think about what you can do inside that chassis. For example, you could have, say, 3 Vertex 7 FPGAs in there with an FMC for your very high gigasample per second DACs or ADCs. You could have a high-end Core i7 Haswell processor in there. Actually, I'll try to use the those are on this side too. Also storage. So a lot of these applications also, in some cases, the storage is often a separate device, but you could actually combine, since you have enough slots, combine, for example, an advanced RAID where you could do your mirroring and striping in an AMC, and a JBOD carrier that can hold up to 8 mSATA chips for up to 8 terabytes of SSD storage in just one of these little guys in there. So with the advances that they have in the digitizers now, you could really get a tremendous amount of performance in a much smaller space. And of course have all the advantages of open standard architecture, where it's modular, it's swappable, multi-vendors, it's not a proprietary solution, and so on. So in the physics world, microTCA.4 has become the de facto standard for the physics community, and some of the converters there are also letting us go to a lot smaller packages as well. In this example, we have 12 channels of ADCs at 125 megasamples per second. And with the form factor for microTCA.4, we're going from the single module to the double module with the RTM. So in this case, we have the 12 ADCs going across from the RTM board to the front, connecting to the FPGA. We also have, in this example, dual DACs at 250 megasamples per second going across the RTM out to the ports out the side. So between the two, you're able to get a lot of performance, and you also get the I/O on the rear, which is one of the requests, one of the requirements of the physics community. So before, for applications like beam monitoring, positioning, and low-level RF, laser, synchronization type of applications, typically this larger type of 8U chassis, 12 slot was a lot more common. Now we're talking about going to requirements where you have, for example, just a 6 slot in a 2U, really saving a lot of space. Actually, one thing that you can do to leverage the hundreds of AMC cards out there is you could do a hybrid of micro TCA.0 and micro TCA.4 slots. So between the two, you could really leverage a very large ecosystem out there for AMCs that have been around for 10 years with the newer cards in the micro TCA.4 format. Also, there are some applications, for example, laser synchronization systems and so on, where you just don't need as many slots. And one thing you could do is you also combine the shelf management functions and an integrated processor within the system itself, not have separate modules. And then you just have two AMCs, and on the rear you could put on carriers for motor stepper drivers, piezo drivers, and so on. So again, you could really go from the very large systems with the new advances in the digitizers to a lot smaller, lot more compact systems designed for swap.